Hello, so we have here two identical pendulums. They are going to be released from different heights. Question: which one will oscillate at a higher frequency? Made up your mind? Let's look at the answer. Well, it looks like the amplitude does not affect the frequency of oscillation, yeah? So this is one of the many interesting things about SHM. The restoring force of each SHM will result in the SHM oscillating at a particular frequency, the so-called natural frequency. So what determines a SHM's natural frequency? Now you have already learned that A is equals to negative omega square x, right? So omega, remember, is related to the frequency of oscillation because omega is 2 pi f. If you throw x to the other side, you're looking at this expression here. What this expression is telling us is that if you can figure out the acceleration to displacement ratio of a SHM, then we would have figured out the natural frequency of the SHM. Okay, I know I started this video talking about the pendulum, but the dynamics of a pendulum is actually a bit complicated. So let's do the spring mass system instead. In fact, we are going to do the vertical spring mass system. So how does it go? Remember, we got a spring initially unstretched, then you put a mass on it. Now, at the equilibrium position, the net force is 0. How come? Well, because the tension in the spring matches the weight of the mass. So I want everybody to notice, for a spring mass system at the equilibrium position, the spring is already stretched. So what happens when the mass is displaced below its equilibrium position? Then the spring becomes even more stretched, isn't it? So the upward tension is now stronger than the downward weight, which means there's an upward net force, and that's the restoring force. Similarly, when the mass is displaced above, then the spring is now less stretched than before, isn't it? Less stretched than when it was at the equilibrium position. That means the tension force now is weaker than the downward weight. That gives a downward net force. So again, you got the restoring force. So this is how the dynamics works. You got this restoring force that keeps accelerating the mass towards its equilibrium position, and therefore is doomed to oscillate forever. Okay, let's do the math now. So at the equilibrium position, the tension force is mg, so that the net force is 0. Now we consider when the mass is at a displacement of x, yeah? So it's displaced from here to here, so it has a displacement of x. At this position, the weight is still the weight mg, but the tension force is no longer mg. It will be larger by the amount k times x. So we are assuming that the spring obeys Hooke's law. Since the extension of the spring has increased by x, the tension force should also increase by kx. So what is the net force? It's just negative kx, isn't it? So again, the negative sign is to tell us that the restoring force is always in the opposite direction to the displacement. Let's bring in Newton's second law. So the net force, we have figured out, right, is negative k times x. Rearrange the equation, we are looking at A is equals to negative k over mx. Now in our mind, we see A is equals to negative omega square x. So what does that tell you? Omega square is k over m. Get it? Because we know that for a SHM, A is equals to negative omega square x. So just by seeing, you know that omega square is k over m. Now of course, omega is equals to 2 pi f, is also equals to 2 pi over t. So just do some algebra and then you can get the formula for the natural period and the natural frequency to be this and this. Now this formula here is derived using the vertical spring mass system, but it can give us a qualitative understanding to any type of SHM. So basically, K is kind of like the stiffness of the system. It's basically the force per unit displacement of the system. So the stronger the restoring force per unit displacement, the higher the frequency of oscillation. The M here basically represents the inertia of the system. So if your system has a very large inertia, then it's going to oscillate at a low frequency. We have here three masses hung on identical springs. So the one on the right is lighter, is more agile, and therefore oscillates at a higher frequency. The one on the left is heavier, is less agile, and therefore oscillates at a lower frequency. And here you see identical masses hung on three different springs. The one on the left is hung on two springs connected in parallel, which makes a strong spring. That's why it oscillates at a more frantic, more enthusiastic frequency. And the one on the right is hung on two springs that are connected in series, which makes it a rather weak spring. That's why this one oscillates at a very lazy, lethargic kind of frequency. And remember, the amplitude has nothing to do with the frequency of oscillation, for simple harmonic motions at least. Alright, that's all. Ta-ta!